Finally, I'd like to talk to you about two types of solids and a unique physical property of water. First of all, the two types of solids are crystalline solids and amorphous solids. In a crystalline solid, the atoms are arranged in a pattern. For example, they're all lined up in nice, neat little crystalline structures in a crystal lattice, a crystal pattern. And this pattern is what causes the crystals to form internally. Here is some table salt. I just poured it out of a container of salt. You see here the Great Value salt. And let's zoom in a little closer. You can see the crystals of salt. Now let's look even closer through a magnifying loupe. You see the itty bitty little crystals? They actually have little tiny squared off edges. They actually make tiny little cubes. Why is that? I mean, nobody sat there chopping these salt crystals into little bitty cubes. What happens is the internal crystal lattice arrangement of the atoms is what causes these crystals to break along the planes of fracture and to make tiny little cubes. The cubes are following the patterns of the atoms that are inside the crystals. Because the crystals are lined up in a crystalline solid like you see here, that's what makes these crystals break into tiny little cubes. All right, the opposite of a crystalline solid is an amorphous solid. These types of solids have atoms that are randomly arranged, and they can very slowly flow. An example would be asphalt. Have you ever seen in the summer you have the asphalt gets kind of a little bit sticky and melty and mushy, especially where they patch the asphalt with just the pure rubbery stuff. So that will get very warm. It won't quite melt enough to become a liquid, but it melts enough to flow. An amorphous solid melts over a range of temperatures. A crystalline solid, on the other hand, melts at an exact melting point, whereas an amorphous solid has a range of melting. And so that's what happens, is a little bit of it melts, but the rest of it stays solid, and it slowly flows. Another example is glass. Have you ever seen a house with old windows where the windows have gotten kind of wavery as time went on, and they're thicker at the bottom and thinner at the top? And that's because the glass has slowly flowed. Or maybe you went out in an old shed, and up in the building there was a glass rod laid across two boards. And so that glass rod slowly began to sink. And that is the glass slowly flowing as an amorphous solid. A fun example of an amorphous solid is cornstarch and water. This is a beaker, and I had some cornstarch, and I put just enough water in here to make kind of a paste. Now you'll notice it's a liquid if you let it flow. But if you put pressure on it, it suddenly turns into a solid. Isn't that cool? So something you can do is pour it out into your hand, and when you roll it up into a ball, it forms a little solid clump. And as soon as you let off the pressure, it starts flowing. Isn't that cool? Notice I can also slap it, and it doesn't go anywhere. It doesn't splatter, because as soon as I put pressure on it, it solidifies. And then I take off the pressure, and then it dribbles and flows. So cornstarch is kind of a fun thing that you can play with at home. You can buy this in the baking aisle at any grocery store, Walmart, whatever, and then you can just mix the tiniest amount of water, add a little bit of water at a time, and then once it gets to just barely enough to kind of wet it all down and just barely flow, you see how hard it is to push this through, but then if you just let it slowly go through, it just drains off like a liquid. But when you put that pressure on, immediately it turns into a solid. Be careful, do not pour this cornstarch and water mix down the drain. It will clog your drain. Instead, pour this in the trash can or dump it in the yard. It's non-toxic and won't hurt anything. It's made from corn. Another thing is, this is exactly how quicksand works. With the quicksand, if you quickly step on it and jump off, it won't let you sink. But if you stand in it for a long time, you'll sink right down into it, and then you can get stuck, and then it gets hard to pull yourself out. Finally, let's talk about surface tension. Surface tension is a physical property of water and some other liquids. What happens is the water molecules are much more attracted to each other than they are to the air or something else. And therefore, the water acts like it kind of has a little skin over the top of it. It just sticks together. So let me show you that with a penny. I have a beaker of water here, and I'm going to add drops of water to the penny. Check this out. See how the water's making a bubble on top of the penny? That's the surface tension of the water. The water is sticking to itself a lot more than to the air around it. Look at how tall that bubble's getting. Isn't that crazy? That water really has a lot of surface tension. Surface tension is why water forms droplets. It sticks together into the droplet. Keep adding some water here. It's getting close. I think it's going to overflow. Oh, there it went. Okay, so the surface tension of water is only so strong, but it's caused by the attraction of the water molecules to each other. Let me show you another example of surface tension. This time we have a cup with water, and we're going to fill it all the way full. Now, that looks full, but we can keep going. Surface tension causes the water molecules to stick to each other and to build up way over the surface of the glass. Pretty cool, huh? Let's keep adding until it overwhelms the surface tension. There we go. Okay, so you see how high up that goes. Next, you can also float a needle on the surface of the water. Because of the surface tension of the water acts like it has a little skin on the top, and you can see the needle floating on the water. Now, something kind of neat is that soap is a surfactant, a surface active agent. So I have a little soap on my fingers. And you see, I didn't even touch the needle, but it sank because the soap is reacting with the surface tension of the water, the surface active agent, and it is destroying the hydrogen bonds, the attractions that cause the surface tension. So let's see what happens now that this is soapy water. Let's try to overfill this cup the way we did last time. Looky there, it's already spilling. Let's get a better angle here. Yeah, look at that. It's barely filled up past the edge of the cup. It's not bubbled up the way it used to be. And so we have destroyed the surface tension of the water. Have you ever seen a little water strider? They go scooting across the water. No, it's not a water spider, it's a water strider. And they go scooting across the water, and they actually use the surface tension of the water to walk on the water. Well, if you put soap around the poor little water strider, that thing's gonna sink. Don't do it because you'll kill it. But that's how it is able to walk on the water, is because of the surface tension.